In this example problem, we're going to be doing some hypothesis testing for a slope. And a hypothesis test is basically there's two outcomes that can happen. And for a slope one, that is, there is a slope or there isn't a slope. So in a hypothesis test, you're basically going through and saying, looking at the information that we have, can we make a definitive conclusion that there is a slope, which implies that a relationship exists between the two different variables? This problem is just a variation of one of the ones that's on your homework, and in it, you're given the simple linear regression results for a data set that you have, so you don't need to go through and calculate all the numbers, you just need to interpret this summary output. And we see from it that our two variables are SMath and SELA, if you will. We are going to predict from this, from 191 schools in the state, the information that we have, how the proficiency scores for the independent variable, ELA scores, affect the efficiency scores for the dependent variable, math scores. And from these 191 schools, we went through and we got a bunch of information, but the one that we're concerned with right now is the slope. And the slope is saying of 0.9067237 that for every additional unit of the dependent variable, the independent variable increases by 0.91, we'll say, percent. Or if you will, for every 1% higher a school has on ELA exams, we are expecting math exams to be 0.91% higher. And we're given all of this information. So when you have a hypothesis test, you have two hypotheses. You have the null hypothesis. In the case of testing for a slope, it's always going to be that the slope is equal to zero. And you have an alternate hypothesis, which in this case is that the slope is not equal to zero, that we have a slope, it could be either positive or negative, that implies that there is a relationship, a correlation between these two variables. So the first thing that we need to interpret from the summary output is what is our test statistic? And the test statistic is a measure of how many standard errors away from the number that you got in your return, your output, would the number in the null hypothesis be? In the sake of this argument, how many standard deviations from mean, if our slope is in fact 0.9067, etc., would it have to be for that slope to be zero? And this is given in the information over here. When we look around, we have a column that's t-stat, and for the slope, it's 24.17. So this implies that if we were going to take a sample of any one given school past this 191, for the slope at that school to be zero, that school would be 24 standard deviations away from our slope, from the average slope between these 191 schools. That is so far away from average. It's mind-boggling. What is the chance that this is going to happen? Well, I'm glad that I asked myself over here because that is the p-value. So the p-value for the association is the probability in this case that you would come up with that point. So a slope that is 24.17 standard deviations from mean. And the p-value that we have right here, as you can see, is 0.000. For the purpose of hypothesis testing, what this implies is if you are going to you're going to reject your null hypothesis for the alternate hypothesis, in this case, state that there is a slope between the two, study a whole bunch more schools and more than 191 we have, and when we come through and get a more detailed set of information, that in fact there is not a relationship between these two, and the slope is in fact the null hypothesis of zero. So the probability that we claim that there's a slope, the alternate hypothesis, and we end up being wrong once we get more information, the null hypothesis, is zero. It's not exactly zero, but it's infinitely small in this case, which means if we make the declaration that there is an association between these two, that the slope is not zero, that we are almost certain that that is correct in this case. And for hypothesis testing, you give yourself some leeway. And in hypothesis testing, you're going to have what they call an alpha. It is your allowance for error. If your probability of making an error, this should be a p-value, I'm sorry. It says test data still, there we go. If your p-value is less than that allowance, which they call alpha, looks a little bit like a fish, you are going to reject the null hypothesis and claim that your alternate hypothesis, the thing you were testing for, is true. So is there statistical evidence that we, in this case, have a slope? Well, it's all based upon what your allowance is for error. And the standard going rate for all hypothesis testing is 95%. You want to be 95% certain, therefore only give yourself a 5% chance of being incorrect. And in this case, if we're going to allow ourselves a 5% chance of being incorrect, and our p-value is zero, so there's essentially a 0% chance of being incorrect, we're way below that allowance that we are giving ourselves. Our probability of error is essentially zero, much less than the 5% that is the standard allowance for error. So in this case, we should, as they say, reject the null hypothesis. I have null in there twice, it's always good. Reject the null hypothesis and take the alternate hypothesis that there is a slope and therefore there is an association. And how are we going to interpret that based upon the data that we have? Well, in this case, we're going to say that there is a slope. And according to the study that we did over here, that slope, 0.9067, etc., implies how much we believe the dependent variable is going to increase for every additional unit of the independent variable. Dependent variable is math. This is ELA. So how much math scores are going to increase for every additional percentage point that ELA scores go up. So down here, we can say that for each additional 1% of students that are proficient in ELA, the percentage of students that are proficient in math should increase by 0.907. Oh, that's not what I wanted. There we go, 0.907%, our slope right here on average. So we've got statistical evidence in this case that there is a relationship between the two, and that the better ELA scores are at a student or at a school, we expect students at that school to have their math scores be higher, although not at the same rate. But that might not necessarily be 100% true. So we are going to want to construct a 95% confidence interval. Well, the summary output has this right here. And we're asked to come up with a confidence interval for a specific X value that we have, and our X value is 55. So we're saying if we had a school where 55% of students were proficient in ELA, our independent variable, what percentage would we expect to also be proficient in math, our dependent variable? And that's these two numbers right here. If using our analysis right here, we had a school that was 55% proficient in ELA. They already took the test. We already knew this. We would expect the proficiency percentage on the upcoming math exam to be somewhere between this number and this number. So down here, we can say that this is somewhere between 43.022 and 46.930. There are two inputs up here for intervals, and while the question doesn't ask, you should know the difference between the two. We have a confidence interval over here, and then we've got our PI, our point interval, if you will. And the difference between these two is that the confidence interval is for a given set, in this case, a given school. So if you were saying if a school had a 55% proficiency in ELA, we would expect the overall proficiency for the entire school to be somewhere between these 2 points. The point interval that we have over here is for one singular data point. And our data point was going through, we'd be looking for a student. So if a student put up a 55 on a test, what do you expect the range to be for the other test for math? And as you can see, it's much wider. So when you're doing a confidence interval for hypothesis testing, usually you're looking for the mean of an entire group, and you're going to associate it with a confidence interval. But you may have things where they're asking you for one individual points within the data, very deep within the data, and you're going to use a point interval. And as you can see, there's a much, much larger range that comes with that.